On UARTS. Okay, well, would you guys like my slides on UARTS then? Is that what you're asking about? Because I
Yeah.
have them. There you go. So, computer communications. Well, okay, you got this computer that can take all this data in and multiply it and add it and do ifs and logical ORs and loops and all kinds of stuff, and then spit data out and control things. Well, you got to get the data in and out of the machine as well before you can work on it. And so it's communication. So you're moving data in and out of the microcontroller, and pretty much, you know, the whole point of a microcontroller is to read some data, process it, spit out a result. And you know, almost all real-world applications would depend on transmitting and receiving data. So it depends on whether you're working on a building control system or a digital projector or onboard diagnostics in a vehicle, MIDI if you're into music. It's all communications, and it's all just moving data in and out. Well, one of the most efficient ways to do it is with a parallel bus. And then we've already seen those ones, presuming you'd seen the earlier lectures, where you've got address buses and data buses, and they're like all going in parallel, all the whole bunch of wires, and they all working at exactly the same time. And so you can move, you know, 1 bit per wire per time. But you typically shorter runs because you got to run a whole bunch of wires, and you start running into all kinds of nasty parasitics and you know, limits on the speed. There's all kinds of electronic-y reasons why you don't tend to get long parallel buses, but you can do it. It's just fairly rare because you got to have 1 wire per everything, and so the long wires get expensive. Olden days, we had Centronics parallel port connectors, or IEEE488, which is a parallel bus. I don't know what you can see because I can't see the feedback anymore.
Yeah, one of those old, like, was it 9-pin connectors?
Oh no, this is like about 30.
Oh, it's 31. Okay.
This is Centronics. This is or not Centronics. This is IEEE488, which is for controlling test equipment. They stack together. Anyway, we digress. So that's parallel. So you got it's all at once. There's the GPIB. I just showed you one of the cables. Many standard parallel buses, but what we're interested in today is called serial communications. That's, generally speaking, where you have your data is transmitted sequentially on 1 pin. Sort of. Serial communications, sending the data as a series of bits, this 1 bit at a time. So you send the first bit, then send the second bit, basically on the same wire. So typically, your wire would be, you know, some voltage level, and it'd be like 0 for a 0 and 1 for a 1. That's a pretty common way to do it, whether your 1 voltage is 5 volts or 3.3 or whatever, or 20 or whatever. It doesn't really matter, but that's generally the idea. Here's a chart that has a whole bunch of serial communications interfaces and properties for them. So they all have different numbers of devices, maximum distances, and speeds.
What does it mean by maximum number of devices?
Well, sometimes it's a point-to-point where you just, I'm a transmitter, you're a receiver, and that's it. One point to point, so there's just 1 and 1. Or in this case, maybe it's 1 on 16.
So like for the USB 127, so that would be like if you had a USB hub, the most devices you could have hooked up to that hub would be a maximum of 127?
Yes, that's essentially the idea.
Okay.
Off of the main USB, yeah. Like if you know, the USB controller can control 127 devices through a network of layers of hubs and stuff like that. But yeah, that's essentially the idea. So you got a maximum, and it's usually tied to how it's addressed.
Okay.
or you know, different wiring situations and different multiplexes. It's kind of complicated, but we'll get there, or at least we'll get part of it. Synchronous. Okay, you got a couple of different flavors. One of them is called synchronous serial communications. And the synchronous communications, you actually have 2 lines, 3 lines if you count ground, and one of them is a clock, and one of them actually is the data. And what happens is, well, we'll see what happens. We'll see that on the falling edge of the clock, the data is free to change. So every falling edge, the data can change, and it can decide it's going to be a 1 or it's going to be a 0 every falling clock. And then on the rising clock is right in the middle after it's had a chance to all settle down and everything. I don't know if you've ever looked at any real waveforms, but they're never quite this square and clean. But basically in the middle of the bit, the clock, you'll have the rising edge of the clock, and that'll just take a little snapshot and say, okay, you're a 0. Decided today that that one's going to be a 0, and then this next one's going to also be a 0. And then, oh, it's a 1 now. Okay, well, now it's a 0. So that's basically the general idea of a serial communication. And sampled on the rising edge, changes on the falling. And of course, you can flip things and make things opposites, and it's always the potential to be opposite day in CPU world. So MSP, that's the device we're playing with, MSP432, has what's called a Universal Serial Communications Interface, and USCI. So you see that abbreviation everywhere. That's the Universal Serial Communication Interface. And it implements 2 different serial synchronous protocols. One is the Serial Peripheral Interface, SPI, and the other one is Integrated Circuits Bus, I2C. My favorite is SPI. I like SPI. It's easy to work with. Slightly little bit more wiring, but it's reliable.
But they both do the same thing.
But they both are basically the same idea. I2C is a little bit hard to work with, but between those 2 protocols, there's like a zillion chips and things. Like get a chip, little module right here. Just happen to have one handy, and again, I can't see what the camera can see, so I'm assuming that's probably about right. That's a 16-bit A to D converter that hooks up with an I2C communication. So I can hook the MSP432 up to this, and I get a 16-bit A to D converter, or a bag of them. Okay. Asynchronous. Well, in asynchronous serial communications, we don't have the clock anymore. Okay, we get rid of the clock. See, in this one, we got this clock on the rising edge every time, so it's like a little, it's all in lockstep, and it's all, everybody knows when to sample, and everybody knows when to change, and it's all good.
What purpose does the clock serve?
Well, it's in this case, this clock is like the metronome, or whatever. The rising edge it's taking is when it's actually looking at the wire. Like it's actually deciding whether or not it's 0 or 1 is as the clock edge rises.
Okay.
Right. All the rest of the time, it doesn't care. The data line could be flapping all over the place, doing whatever it wants, but only during that instance, during that clock rising edge, does the flash bulb go off, and it takes a picture of the line to say, okay, it's a 0 now. All the rest of the time doesn't matter.
Okay.
Okay, and so that allows, so the transmitter knows this, so he can say, okay, clock low, change, clock high, okay, there you go, clock low, change, clock high, there you go, and you can just clock out the data as you want, and whatever the data line wants to be while the clock's going, that's what you get. And on the receiver is actually receiving the clock as well as the data. And so it can say, okay, well, when I see the line go high, that's when I'm going to look, and it's perfectly synchronized. We're synchronous.
So basically, with synchronous, you're not having to send like packets, right? You can just send constant information as long as there's a clock pulse that it can detect it and change.
Well, that's sort of packets are sort of an expanded idea. This is
Okay.
lower level than that right now. We're just talking about just getting the data across. We're not really talking about what shape the data is in.
Okay.
Okay, so for now it's just arbitrary data. We don't care.
Okay, makes sense.
The important concept is that it's synchronous. So it's got a,
I thought packets was more to do with the internet.
All of the soldiers' feet are all landing on the ground at the same time. It's synchronous. Both sides, the receiver and the transmitter, are in lockstep with each other and can tell exactly where they are.
Okay, makes sense.
Now we got asynchronous. Now we just figured out how important this clock is. We're going to look at asynchronous serial communications. And the trick with asynchronous serial communications is it throws the clock away. It says, well, no clock anymore. We get rid of it. Well, we just figured out that was super important. So how are we going to do that? Well, we're going to throw away the clock. So we only got one signal now. But we're going to throw in some extra bits, framing bits. We're going to add a start bit and a stop bit. And we're going to decide that when the line is high, it's idle. The first time that the data goes low, that'll be the beginning of our start bit.
Yeah.
Okay, and that's going to be our little assumption now. So there's no clock anymore. But what happens is we didn't really get rid of the clock. The clock's still there because it's super important. But what we did was we just made there's no clock wire. There's no way to. There's actually two clocks now because there's one on the transmitter and one on the receiver. And we got to make sure that they somehow get synchronized. Once they're synchronized, we can run a clock at a steady enough rate that at least over a short period of time, we can pretty much guess where those edges are going to be. Okay. I can't quite remember what I was meaning with this one. I think this has to do with the fact that,
so UART is asynchronous, which is what we're learning today.
You betcha. UART.
Okay. And then
Jump to the punchline there.
So the pyramid thing, like what is that supposed to
Well, what I think that has to say, and it's been a while since I put the slide together, so I'm not really sure, is really we don't really know where the 0 is in there. We don't really know where the 1 is in there. It can be sort of anywhere. Like this is the data we got showing up. We see this is the start bit, and yeah, really it's hard to. It gets fuzzy as to where to call a 0 and where to call a 1 because we don't have a clock anymore. Anyway, same protocol that COM ports are going to use. So RS-232 ports, RS-485, which is a common industrial network for machinery, RS-232 for terminals and all kinds of other stuff, very common. They're all basically your COM ports. You used to have serial ports at the back of your PC before USB. Used to have individual ports, and they were RS-232. Okay, so we've got the two different kinds. We got asynchronous and we got synchronous. The advantage is that the asynchronous has no clock signal, so you got one less wire at least, and the synchronous serial is it has the clock signal, but it's very much a simpler device, so it's a lot easier to build, a lot less gates, a lot less power, or whatever. Disadvantage though is the asynchronous. You got to have a bunch more circuitry in order to actually synchronize to the receiver and get the clock rates to match, and you have to agree on a bit rate ahead of time. In the synchronous system, basically the data speed is completely governed by the speed of the clock, which doesn't even have to be constant. It could slow down and speed up because it's only on the rising edges that it's going to actually sample, so you could run it at any speed, and as long as the parasitics of the actual physical connection were acceptable enough so that you could actually see the change by the time the clock edge happened or whatever, and you were able to pull the clean edges out of the noise or whatever, you could run it as fast as you want, right? In a synchronous system. But in an asynchronous one, the faster the clock rates are, the harder it is to actually keep them in sync. So there's a bunch of types of connections that you can have. Okay, a full duplex is like, you're golden. It's great. In a full duplex one, you have each device has a transmitter and a receiver, and it's point to point. So devices 1's transmitter goes right to devices 2 receiver, and devices 2 transmitter goes right to devices 1 receiver, and they're just always hooked up. And drivers are on the right ends, and it's all working. And with that one, you can actually send data both directions at the same time, because you have a separate wire for each channel. And so you have a separate wire for transmitter and receive, and you can send and receive at the same time. Well, wire's expensive, so maybe you want to try out a system called half duplex. And in half duplex, you have a single wire that's shared between the transmitter and the receiver. But with this one, you actually have to take turns, because you got to share the wire. So you got to have a little switch here that says, okay, well, I'm going to be the transmitter now for a while, so you better be the receiver, because otherwise we got a problem. So I'm going to send some data to you, and then you're going to do whatever you want, and then maybe there'll be a mechanism that says, well, now it's my turn to transmit, and you better start receiving. So then use the same piece of wire to send the data the other way. So you're just taking sharing a turn. Common way to look at that one would be like a walkie-talkie with the push-to-talk button. Only one person can talk at a time. Everybody talks at the same time. Nobody hears anything. So you got to coordinate the bus switching. Another way of doing it is just called simplex, and that's just a one-way where I can send stuff out, and like now, I can't even tell if you're hearing or not, because it's just silence on the other end. So I'm assuming you guys are still there and the network's still up.
We have better than simplex right now. It's okay.
It's all good. I mean, I don't even know if the video is working or not. I just see the PowerPoint slide thing. Okay, so yeah, okay. Single wire that's only transmit and receive, and it's one-way communication. So you really, you gotta trust that the other side's, still there, right? So that would be done for this one. Okay.
I don't know if I get the serial pour though. Oh, serial pour. Got it.
Yeah, there you go. Nice fake laugh.
No, that's his laugh.
Good.
That's John's laugh.
Okay. So, first thing we want to talk about is character framing. Well, generally speaking, we're going to be sending bytes, just because that's a good place to, well, whenever you're communicating, both sides have to agree on like the language you're going to speak and the format you're going to speak and all that stuff. And one of the most universal chunk of data is typically a byte, 8 bits. And so that's when we're talking about a character. And framing is going to tell us where one byte ends and the next byte begins. So we're going to have a start and stop bit. And they're going to guarantee at least one transition per frame, which allows the receiver to synchronize to the transmitter's clock. And what that essentially means is the line is idle, and we're going to be guaranteed to get at least a start bit, because we're going to get a falling line, because that last stop bit put the line high again, and we're guaranteed at least to get that falling edge. minimum framing, 1 start bit, 1 stop bit. Sometimes you can see 2 stop bits. I don't think I've ever seen 2 start bits, but I've seen 2 stop bits. Adds a bit of overhead. So for 8 bits of data, you're going to have a 10-bit frame, right? 1 start bit, 1 stop bit, plus your 8 data bits, so it's a 25% overhead. And if you want to put all the framing stuff on and all the bells and whistles on, then you're going to get 1 start bit, you're going to get a parity bit, which we'll talk about at one point, and 2 stop bits for every character. So every 8 bits is going to have an extra 4 bits added to it, just automatically by the UART itself. And that adds a 50% overhead to an 8-bit character, which, you know, you may or may not be able to take the hit depending on the data you're trying to send and how fast it has to get there. Like, if your goal is ultimate speed, then you probably don't want the parity bit. But if you can run it really slow and your goal is more to have a higher reliability, then the parity bit obviously becomes an obviously good addition.
Does the communications port on the MSP like automatically contain parity bits?
The Universal Serial Communications Interface device on the MSP 432 slices, dices, makes French fries.
It's got everything,
a seat warmer, whatever.
Okay. Cool.
So parity bits, an extra frame is added for error check, or extra bit is added to the frame for error checking. So, and you got 2 different kinds of parity. One is an even parity, where the extra bit is such that when you add up all the 1 bits in the data plus parity, it's always an even number. And then odd parity is basically the opposite of that. So if we were sending a data 0 of hex A5, then the bit pattern we'd be sending would be 1010, 0101, and we'd add the parity bit to that. So 1, 2, 3, 4 1 bits. And if we had odd bits, we'd want to, 4 is not good, so we want to make parity be a 1. That makes it a 5, so now parity is odd. And obviously the opposite for the opposite. Okay, so typically if you're looking at oscilloscope, which is, you know, how you can see these things, because blinking lights don't do it to you, work too well for seeing serial data. But if you're looking at it on a scope, you're going to see something like this. So the line's going to be a 1, solid 1, all the time, all day long, until a character comes along. And when the character comes along, we're going to get this falling edge right here. And that's what we're going to use for our synchronization. But once we know we've got this falling edge, we've already agreed on the speed and the number of parity bits and the number of start bits and stop bits and all that stuff. And so the transmitter and receiver both know that ahead of time. And so we can actually infer where all the other clock edges are and extract our data. And when we finally get to the end, we have a final stop bit, and the line goes back to high for as long as it takes until another character comes in, and that's the start of the next character. So it'll be idle, get our start bit, and then we'll get the lowest bit to the highest bit. And then we get our stop, and then it goes back to idle again. And I think you can swap that around because, as I said, it slices and dices, but I'm pretty sure, although, like I say, it's often opposite day, especially for lefties like me. But I think this is actually officially what you get for the standard is the lowest bit first, but I have to double check that because I refuse to memorize stuff like that anymore because I always get it backwards half the time. Okay, so how do we do the synchronization? What's the trick? There must be a trick. Well, basically the trick is to take that synchronization edge, that first falling edge, and we're going to say, oh, okay, well, that's our start of our sync bit, or sync bit, or start bit. That's the beginning of our start bit. Well, we already know how long a start bit is because we've agreed on the baud rate. So we know how wide a start bit is, what one bit time is. We know how long that is. So why don't we take half of that time? And then we'll call that our synchronization, like synchronize our clock to that so that it's our clock synchronizes to the middle of the start bit, half of a bit time after the falling edge. Now we can look 1 bit time down the road, and we should be right in the middle of our first data bit.
Sorry, does that mean that it's only like testing that often, or is it like always receiving, or does it do like a test for that next bit and the next one, or?
Essentially, it recreates the clock signal.
Okay.
Such
and then it would like, yeah.
That would be the rising edge of the clock right there. It says okay, and then the falling edge could be here because we already know how big a bit time is.
Okay.
Right.
If
So once it has that.
If you're pointing at the screen and we just can't see it, just so you know.
Oh, okay. Sorry. Oh, I'm pointing at the wrong. I'm pointing at the wrong screen. That's why. Oh, geez. Okay, sorry. It's I'm still a little new at all this stuff. Okay, sorry about that. It's probably been about half an hour now, right? I can see it on my screen fine. Okay. So there's our falling edge, right? And we know how long a bit time is. So all we're going to do is decide half of a bit time from there. That's where we're going to synchronize our clock to. And then, so that means that the falling edge of the clock will be here, and then this will be the rising edge of the clock where we're going to see the 1. And then we're going to get a falling edge of the clock here, and then this will be the rising edge where we'll see the second 1, and so on until we see our stop bit, and it goes back to idle, and it's a little state machine thing. So we have this enhanced universal serial communications interface, and it's a device on the MSP432, and part of it has a UART mode, and with the UART mode you can do 7-bit or 8-bit data, so you can actually have a 7-bit data instead of an 8-bit data, because what you use that for is 7 bits plus parity is usually what you see in that way. It's still a byte. It's just you've thrown away one of the bits of data. Either way works as long as both sides agree. It's got independent transmit receive shift registers, so you can do a full duplex connection and be simultaneously sending and receiving data, and they just work. Separate transmit receive buffers. You can do least significant bit first or most significant bit first, depending on which way you want to do it. So you can either have shifting from B0, B1, B2, or you can have B7, B6, B5, your choice. And it does have some hardware mechanisms for detecting idle lines and detecting break and detecting a couple of other strange situations on the line, and also mechanisms for doing addressing in multiprocessor systems. So if you want to do one UART connected up to a whole bunch of processors, you can have ways of addressing them and doing tricky protocols. And there's hardware to help you. Programmable baud rate, so you can basically program the baud rate to be basically anything. It's derived from the CPU clock, but it's just like the other ones where you can hook it up to whatever clocks. There's a bunch of different clocks, and depending on how slow the clock is, you get more and more limited to your baud rates that you can choose based on their accuracy and stuff like that. But it's essentially, you can think of it as being able to do almost any baud rate you want. A bunch of status flags, and has a bunch of interrupts. So you got interrupts when it receives a character, interrupts when it's ready to transmit another character. You can get one when the start bit's received or when the transmit's complete. I never use those ones, but typically receive and transmit you can use all the time. Here's what the device looks like. And after looking at the timers and the A to D converters, this one's probably not looking quite as scary, I hope. assuming you actually looked at them. But it's broken down, so you got a receiver. So this up here is all to do with receiving. So there's the receive pin right there. And essentially, you're pulling data out of this register right here. And this is used for the shifting and the parity, and got a bunch of the IRDA, I think, is an infrared protocol that I don't know anything about. But this will magically help it along. The clocking. So again, you can select, the system clock or A clock or U clock, and it's got a prescaler and a modulator divider, and then we're going to go through some math on that, and then that will derive the receive clock and the transmit clock, and I believe they both have to always be the same. I think that's what you got going on there, is unless you're doing some half duplex protocol or something like that, which in case you could make them. You could switch the clock on the fly. But in general, if you're trying to run the receiver and the transmitter at the same time, then they both have to have the same baud rate. If you really had to do different baud rates simultaneously, you'd basically put them onto two separate EUS, like two different USEIs. I think the MSP 432 has at least 2 of them. Might have 4 of them. This bottom part is the transmitter section. Basically, you are dropping data in here, and then it goes into here where it hits the shift register, and then it gets basically shifted out this pin here, and it's got an encoder for this decoder up here, and it's got a state machine for adding the start bits and the stop bits and all that other junk parity and what have you. There's a receive buffer, so that's where the data is gonna come from. And there's a transmit buffer, there's where the data is gonna go. So the data is gonna be on this line here, and it's gonna do all the start bit and all that other stuff. And once it finally finishes clocking all the way in, it'll pop a byte up here. And once it does that, it sets this flag to say, hey, there's a byte there waiting for you. Down here, what's going to happen is you're going to drop a byte into this buffer. It's going to go into the shift register and start clocking out. And once it's finished clocking out, well, actually, sorry, it's a little subtler than that. You're going to drop a byte in here, and it's going to go into the shift register. And as soon as it goes into the shift register, this buffer is now empty. And so this flag goes on saying, hey, I'm ready for you to drop another character into this buffer. But this is still being shifted out. And so until this is all shifted out, it stays that way. And then as soon as the last bit goes out of here and then you get the stop bit, then this byte goes transferred into this register, and this flag goes back on saying, hey, ready for another one. So you're always kind of got a little buffer. Same thing here. You got a receiver, a byte being shifted in, but it's not until it's all shifted in that it pops into here. And once it pops into here, you get the flag saying it's there. So it's kind of the opposite.
I'm getting the feeling that you can't really do serial communication without interrupt vectors and stuff.
Well, you can indeed do polling. And at slow speeds, and if you've got the horsepower to spare, then polling is fine. I do it occasionally, depending on the application. In a medium performance system, you definitely want to have some interrupt mojo happening. But if you want truly high speed, then you're going to use what's called DMA, which is direct memory access. And that's really cool when you get it working. It's great. It's a little tricky, but it's great. What happens with that is you end up setting up, like, okay, say you wanted to transmit 100 bytes out the port. Well, with DMA, you can basically say, okay, there's 100 bytes over there, serial port. Send them and let me know when you're done. Is effectively what you get. You get one interrupt at the end of the 100 bytes.
Okay.
Okay, that's when you're doing it right, that's what you get, right? but it's tricky to get there, and you're a ways away. But yes, you can do an interrupt with single bytes. Every single byte you get an interrupt, and you just handle it. Say, oh, I received one. Put it where I'm going to put it. There's the
Reset
interrupt.
the flag.
Reset the flag, and it's the same thing as getting a push button.
Okay.
Right? You got to figure out where you're going to put the data, but otherwise, once you've put the data, once you've pulled the data out of that receive buffer, there's now room for the next byte to pop in a little while later. And so you pull that byte out, put it into wherever you're going to do whatever you're going to do with it. And the same with the transmit. You can have a little pointer that walks through a string or something and says, okay, counting out 100 bytes. So here's the first byte. You drop it in, and then you wait for an interrupt. And when the interrupt happens, you say, okay, well, here's the next byte, here's the next byte, here's the next byte, and so on and so on.
And this lab kind of focuses on just communication between the computer and the board, right? Like manual selecting when you can send the data, I think.
Yeah. Well, yeah, essentially. You're just basically, just like the A to D converter, you're just trying to get a rise out of it.
Mm-hmm.
Just kind of trying to make it do, something.
Yeah.
Okay. But when you actually want to use this thing for real, you start getting into the a lot more. I always call them channels, but you could call them ring buffers, and there's several mechanisms for buffering data in and out of this type of thing that are software mechanisms that are beyond the scope of this course or beyond the scope of this talk or whatever. Suffice it to say, this is basically this dance on the byte level is what has to happen. Whether you're doing it with busy loops, while the flag is not set, wait. Oh, the flag got set. Put another byte in. Go back up. While the flag's not set, wait. And you can just sit in a while loop and do that, and that's perfectly legit. Trouble is, you're not going to be able to do anything else. So it depends on what you're trying to do in your system. If you're really trying to get the whole multitasking thing going, you don't want to have a lot of busy loops and things like that. So, but again, that's out of the scope of the course. But the dance with the flags and the dropping the bytes in and out of the registers has to happen either in main in a busy loop or under interrupt, or basically DMA does the same thing, only in hardware. Okay, so just like the timer and the ADD converter, you must be getting used to it by now. You're going to get a page full of
tons of registers.
Page full of registers, right? But if you're starting to pay attention, you're realizing there's like patterns. You're going to see this, UCAX in front of every one of them, and CTL. You've seen that one before. You almost know what CTL 0 and 1.
This was kind of my struggle with the last one. Is that there's so many different little registers that you got to figure out how to write to each one, and I guess it's kind of the same each time, but yeah. Yep.
Yeah. No. Once you've seen the first one and gotten past it, and seen the second one, and you get to the third one, and start to see the pattern. And you realize they're all a bunch of details and stuff, and they're all got their own special little story, but they're all kind of the same. And it gets quicker to figure out what they're going to do and what you need to do with them, because they use the same. They're like UCAX IFG, right? The interrupt flags. You know what that does. You don't even have to look it up.
Yeah.
Right. UCAXIE, interrupt enable. You know what that one does.
Yeah.
Essentially, I mean, you'll want to look it up to see what flags mean what. But as far as the basic mechanism of the register itself, you know why you want to look for it. You know why you want to go to section 24.4.10, because you want to figure out what flag is what, right? But the flag thing is not going to be a surprise. Okay, character format and options. So this is basically a way of looking at the character format. We got our start bit, our data. There's like I say, there was that address mechanism, so you can have an address bit, optional data bit, optional 8th data bit, and then 1 or 2 stop bits, parity, Start bit, 7 or 8 data bits, an address bit if you're in address mode, even odd or no parity, and 1 or 2 stop bits. And that's 1 character. And you can set whether it's high bit or low bit. Okay, well, the trick for finding this clock rate that they use to make it so it's like, how are you gonna, now that you're trying to synchronize this clock, okay, we've already figured out we want to synchronize the clock. Well, how are you actually going to do that? Like, you're gonna have to figure out a way to force the edge to be in an arbitrary starting spot. It's you know, some analog thing that slows it down until it synchronizes, or speeds it up until it synchronizes, or it's a phase lock loop, or all kinds of strange mechanisms that you could do it. But this is what they actually do, is they have what's called an oversampling clock. And what an oversampling clock does is it runs at like 16 times the baud rate. So every bit you're going to get 16 clock cycles worth of sorry, I'm pointing at the wrong screening. Every bit you're going to get 16 bits worth of clock samples. So if you look at the 1 bit period up here, that's like the same as 16 bits, 16 cycles of the clock. So this is running 16 times the baud rate. And essentially the rising edge of this clock is used to look at the received data. So on this edge, we see it's a 1, and on this edge, we see it's a 0. But when we hit this edge, we see, oh, data's gone to a 0, so we must have got this falling edge. Okay, so now that we've seen that, all we're going to do now is just we're going to count 8 cycles. And once we count those 8 cycles, we're now in the middle of the start bit. So we know where the middle of the first data bit is going to be, and we know where the middle of the next data bit is going to be, because they're going to be 16 cycles away, because it's running at 16 times overclock. And it's just a little state machine. Tricky?
That's a little bit to grasp.
Well, I mean, you see how it's how like the difficulty you'd have trying to synchronize the clock any other way, or other ways.
Yeah.
Right? Like to actually try and get those edges to be exactly the right, you would have to slow the one down until they're right, and like phase lock loops, or I mean, I don't know how much of this stuff you guys have done, but trying to change an oscillator is tricky.
Mm-hmm.
Well, this one doesn't actually ever change the oscillator; it just runs at 16 times the speed.
Yeah, makes sense. Okay.
And never has to change at all. It's just rock solid, and all you're doing is a state machine to decide, when you're going to care and when you're going to look out of these, out of the 16 cycles. You think, okay, that's where we take our sample, and there's where we take our next one, and blah blah blah, and it's just straight counting. Okay, so you need to do baud rate calculation. So you want to connect to the virtual COM port. Okay, now your whole lab, you're going to do the virtual COM port. What happens is on that one, oh, I don't even know if I've got a board handy. There's one. No, it's not even the right board. Okay. Anyway, you're going to plug your USB from the development board into the computer. And when you do that, it's actually going to create 2 COM ports. And they're virtual COM ports because they're not actually there. They're built into the USB. So it looks like 2 devices of those 127 we were talking about. And one of those devices is basically talking to the debugger of the processor. So that allows you to load programs and single step and read registers and read memory and change registers, whatever you're doing. And then the other one is a user COM port. And that user COM port is hooked up to the UART. And if you actually look at the schematic, you can actually figure out which UART, which pins, and all that stuff. And it actually shows up the in the middle, you have this like whole row of jumpers that are all stuck together. Well, those are jumpers for power, and some of those are connections for the debugger. And a couple of those you'll see, well, I don't actually have the real board here. Basically, you know, it'll say TXD and RXD basically on this one. Probably the same on that one too.
TXD,
So,
RXD.
yeah, and those are basically the circuitry on the top half of the board will interface to the USB and basically create a real UART, and that real UART basically shows up on those two pins, TXD and RXD. And then those two pins are connected to the UART, that's the real UART that's on the MSP432 on the bottom half of the board. And it's just a full duplex connection with just like what we did, where the transmitter is hooked up to the receiver and the receiver is hooked up to the transmitter. And that's what you get. You get that for free. It's part of the development board. And what the lab is going to be doing is firing up the UART that's on the MSP432 and then hooking up what's called a terminal program on the PC, which emulates one of those old, what was the bank again? You know, with the terminal, you've seen the terminal with the screen and the keyboard, and they're like at airports and banks and stuff like that. And they're just text. It's old school. You still see them. They modernized it by getting rid of the actual terminal that only did that and put a PC on it and then ran a program that emulated that. And what you're doing is you're doing the same thing. You're emulating a terminal. A virtual COM port that's hooked up to a physical UART on the one chip, and which is hooked up to a physical UART on the other chip. So I'm going to connect using the virtual COM port over USB at a rate of 9600 bits per second, which is a very standard speed. The number one format that you're going to get pretty much everywhere is 9600 baud, 8 bits, one start, one stop, no parity. Okay, so here we're going to do the calculations. We already know what our crystal frequency is for our system clock, and we want to get a oversampling clock at 16 times 9600. So 16 cycles per bit, 9600 bits per second. We're talking 153.6 kilohertz. So we're going to take our 318 megahertz and divide it by 153.6 kilohertz. And we're going to get this fancy number, 19.6484. So say we're going to use 20 for the divisor. If we use 20, then our final clock would be 94.31 bits per second, which is not really what we're after. Like 1.75% error is like, you know, quite a bit of error there. And what happens is if the clock is running a little faster or slower, then the more bits you send out, the more chances are that your edges are going to drift from the middle of the bit to closer to where you're running into the parasitics if the edge is not falling straight down, or it's a little rounded, or not quite the threshold and the quite time. So you got to watch out with the error. Smaller the error, the better, obviously. So we're allowed about 2%. We're pushing the 2%. So we could get away with this, but it wouldn't be really very good. Well, there's a mechanism for adjusting no, I'm pointing at the wrong one again. There's a mechanism for adjusting the this error. And we can adjust it using the UCBRF register. And what that does is it gives us an adjustment of 16ths. Because it's all got to be done in decimal. Like in Digi anything? Did you guys ever do a divide by 19.66484?
Yeah, no.
No, you probably didn't even do a divide by 19.
Nope.
But you could do a count to 19 pretty easily, and that's kind of the same thing, right? You could make a counter that counted up to 19, and that would effectively be your divide by 19. But that 6484 business is probably not just not going to happen, right? Well, the trick they have here is that they allow you to actually specify this 0.6484 in terms of sixteenths. You can actually use a divisor of, let's go backwards. So we can actually use a divisor of 10 sixteenths. So we have 19 and 10 sixteenths instead of 20. Now we can get our error down to less than a tenth of a percent. Okay, so it's this 16th bit. So you got two divisors. One is the 19, that's like a coarse, and then you got like a fine adjustment that's measured in sixteenths.
Okay.
Okay. So this just improves the error. I mean, even though 1.75578% is kind of okay because we're allowed to have 2%, but you start putting it on a longer cable, or you start, wires aren't twisted properly or something silly, then you start pushing close to the limit there. Your edge rounds out a little bit, or you want to get your speed up a little. You say, oh, well, 96 is no good. I want to do double it. I want to go to 19.2 or faster. And now all of a sudden this error is way too much. Okay, the UART pins are actually on the PC, or on the CPU. And I must have showed you this diagram at least once already. And so you can kind of read it already, right? You got, this is either port 10.1, this is port 10.2, and then UC is the Universal Communications. That's what we're talking about. And it's B3, and then this is the clock pin.
You're pointing at the wrong page.
Yeah,
again.
I'm pointing at the wrong picture. Sorry, it's the camera's over here, my picture's over here, and my mouse is over here. So sorry about that.
No problem. I think we get what you're talking about too, though.
Yeah. Okay. So this is like P10 right here, right? And this would be UCB 3, and this is like the clock pin. Right? This is
Okay,
like,
that's the actual clock pin in the UCB or the
of UCB 3, of UCB 3,
okay.
right?
Yeah.
Like all of a sudden makes sense now, right? Now we can read this one and say this is like either port 10.2 or it's the UCB 3, and this is slave in, master out, which is the SPI port, which we'll talk about, or the SDA, which is the I2C version of it.
Okay.
All right. One we're actually interested in is down here, and we got P1.2, and that's UCA 0. I'd probably have to go to the data sheet. I think there is like four of them or something, or a bunch of them.
Four different communications.
Something like that. I actually go look it up in a sec, just to give you the straight answer. But it's a bunch. It's not just one.
Okay.
Obviously two, but it could be even more. But here's RXD, and the one below it is UCA 0, and then it's TXD. So receive data and transmit data. And that's our UART right there, those two pins. So you can poke a scope pin on them. You can actually look at them. You'll actually see that they go up to this little jumper bar thing. Oops. So you got to connect the application to UART. And we got to, okay, we're connecting up the internal peripheral and not using the GPIO anymore, so we don't want it to be P1.2, we want it to actually be the peripheral.
Okay, so this, yeah,
so
it's
we
like
have to,
okay, like the secondary options for those pins, just like we did with the ADC and
Yep,
the other
yep,
ones.
Yep. So it's the same thing, like same thing again, right? So once you kind of learn how to do it once, it's just kind of, you can make guesses on how to do it the next time, or at least, you know. Okay, so to initialize the EUSC guy, we're going to set this USC reset in control 1. We're going to set that pin, and that's putting in the clutch, like what we talked about with the A to D converter. Right, you're putting in the clutch. You're waiting. You know, you're saying, okay, we're going to make some changes here, so don't be running anymore. Just shut down a little bit. Don't power off, but don't be running the engine. And so we have to have this bit set to 1 for the whole time that we're setting stuff up. That's holding in the clutch. Going to configure our select bits like what we just said, and then we can set the baud rates and everything like that, and whatever other settings, clocks. Use this clock, use this divisor, use this 16ths, you use this parity, bit width, bit order, blah blah blah, and then we clear the reset bit. This is kind of what the code would look like if you were doing it in polling mode.
Sorry, could you drop back to that last one for just 1 sec? Thanks. Okay.
Yeah, so you put the clutch in, you set the baud rate, you set what all the control registers, all the binary bit orders and parities and stop bits counts and all that other stuff, and then you configure it as
Now this one's slightly different from the ADC though, because you have to configure the ports like with the initialization, or not really, kind of the same thing still.
Well, you always got to initialize it at least once, unless they happen to be in the right order. So
I'm just thinking for the ADC one, like we had to initialize the ports on a separate, like not in the.
Oh well, with the ADC one, you were kind of cheating on changing the channel for doing multiple channels, and in which case the easy sort of, like, you wouldn't necessarily do it that way in a real product.
Yeah.
Right. It would it's a lot of overhead and it's a little clunky. It's fine for doing a joystick, and you could use it for a joystick forever. It wouldn't matter. No, nobody's gonna, you used extra clock cycles. Oh, but in a real application, you typically want to try and make things efficient, and you're trying to serve battery, and you're trying to make it simple and all this other junk. So you would have different mechanisms. So it was really just for the lab or for lower performance type applications.
Okay, sounds good.
Generally speaking, when you're going to use a device, you're going to configure it once during reset, power up, set up your UART or whatever you're doing once, and then after that you would be in a using it mode.
Mm-hmm.
Now, if there's some sort of the way your application works or your device works in such a way that you need to power it down or something, and you leave it powered off for a bunch of time, and then you power it up and do things, then you might need to reinitialize it. There are some CPU low power modes where you lose initialization, and so you have to reinitialize them when you come out of that low power mode, but we digress. In general, set it up once and then start using it. You never really have to set it up again. Obviously, on a UART or something like that, if you want to change the baud rate, so you have a protocol that says, okay, well, our standard is that we talk at 9600, and then once we connect to 9600, we can say, hey, we're really smart, let's go to a faster speed, and both sides can then switch speeds at the same time and run at the higher speed from then on and do all kinds of weird stuff like that. Then you can change the baud rate on the fly, but you have to basically put the clutch back in, change the baud rate, and then let the clutch out again.
So generally, probably the better operation for that would be to put like each of the different initializations into a separate function, and then call on that function when you want to run at that rate or something like that, right?
Yeah, you make a function called setBaud, and you pass in the number, and it does the rest.
Yeah. Okay.
And when you're trying to make functions, you want to think in those terms. You want to say, I don't really care what the details are. Like, I don't care that setBaud has to put the clutch in. That's not my worry. I'll worry about it while I'm writing setBaud rate. While I'm creating that function, I'll worry about it a lot. But as far as somebody who's using it, they don't care nothing about that. They just want to go set baud rate. Here's the baud rate. Just do whatever you got to do. Let me know when you're done. Come back when you're done. That's it,
okay.
Right? And that's how you want to do your functions. You want to be at a little higher level. Anyway, this is an example of code, a one-pager. It's basically doing this 19 and 10/16 that we just talked about. So there's the baud div, there's the fraction. So there's the 19 and 10/16. And there's our main spot to hold some data. The watchdog. There's our cell. Putting in the clutch. Then we're going to set up, okay, well, CTL W0, well, W0 is CTL0 and CTL1 as a 16-bit register instead of, or as a 32-bit register maybe.
Oh, you can do that?
Well,
okay.
So this is like a byte offset.
Yeah.
Or
yeah, and that one just says control word. Okay.
Yeah.
So it's controlling both of them.
Yeah, and it just is both. You can either say this one to just do the low one or this one to do the high one, but this will do both at once.
So then those must both be 8-bit registers then, right? Because the word
I think so. I'll have to look it up. I always,
Yeah.
like I say, I always double check stuff like that. But that's essentially the idea. This is half of it and this is the other half, and they both combine into one. And you can see the same thing here and the same thing here.
So if you want, you could write to just one of them, or you can write to both of them at once.
Yeah.
Okay.
Yeah.
The ADC doesn't have that though, does it?
It might have one or two of those. I'm not sure. You have to look it up.
Well,
code. There's our setting the W. Okay, now here we're just or equaling, right? So that's just going to set that one bit. We don't care what the rest is. Here we're doing an equal. Now when you do the equal, you basically are setting all the bits. So if it's a 0, it's a 0. If it's a 1, it's a 1. You're setting everything. Okay? So when we do that, we want to make sure we also still have that reset word into the thing we're setting. So keep that bit set so that keeps the clutch in. And then we're going to set our baud rate divisor. And now for this one, this bit right here is setting that it's using the oversampling mode, the oversampling 16 mode. And then we're going to OR it in with this calculation. And this calculation is our baud rate fraction, but we got to shift it by a little bit because it's actually a few bits up. I could show you a picture of that. It's not as tricky as it seems. And then here, we're clearing the reset. We're letting the clutch out, letting the machine kick on, and then we're going to fall into our busy while loop. So here, we're going to say, well, this flag is not set. Well, the RX flag is not set. We'll wait for this flag to come on. We're just going to sit in this busy loop until RX-IFG is set. And once it is set, then we know there's some data waiting for us in the RX buffer. So here's for the EUSCI A0. We already looked at those pins. We already know it's A0. Here. So that's why we're, it's EUSCI A0 all the way. And then, so we're going to get the data out of there and throw it into our data place right now. We're just going to store it into that variable. And then we're going to go into this busy loop where we're going to wait until this flag gets set. And when that flag gets set, that tells me that there's room in the TX buffer to set some data. And I'm just playing games now, so this is not just echoing the data straight back. I'm actually changing the data that I send back so that it sends back something different.
Oh, okay.
It's arbitrary. I'm just playing games. I don't even.
Okay.
Okay. So that's basically your instance step to code. Now in a interrupt situation, some of this stuff might actually happen in interrupt, and instead of having these busy loops, they would just be the busy loops would disappear because essentially you'd be getting interrupts.
Mm-hmm.
Maybe main ends up with an empty while again.
Yeah. Now, sorry, so is there like another, like a start transmission one as well? A bit for this one?
No.
Okay.
No, you want to transmit something once you've done all this setup. If you want to, you get down to where this while is. If you've let the clutch back out, all you got to do to transmit something is drop a number into this buffer, into this register.
Oh, okay.
And whatever you drop a character in there, an A goes out as an A. It's done.
Okay.
And you got to wait for that register to be ready with this line above it, right?
Okay.
Because if you just drop another number in there right away,
you're going to mess it up.
You're going to write a new number on there, and eventually what will happen is the shift register will finish shifting its stuff out, and the new number will drop in, and it'll be whatever the last write was.
Yeah. Okay.
So you always got to wait for the flag. But essentially, if you're doing it in interrupt, the flag you won't be there unless that flag is set.
Mm-hmm. Okay.
Straightforward?
I think so.
Okay. So typically what if you were just going to keep in this pulled mode, you could take these two out and make them into their own function called receive character. And maybe take these two and make them into their own function called transmit character. Put car.
Yeah.
Put car and get car.
Yeah.
And they're pulled. So they are what they are, but at least you've got them abstracted into something that's later on you can actually replace the behind get car and put car with whatever you want that uses interrupts or DMA or whatever you need. And anybody that's using it is just calling put car.
Okay.
All right. So with that in mind, I throw in this bit of bonus code. Okay, ready for the bonus code, everybody? Woohoo!
Okay, so just like put string function.
Yeah, that's a put string function indeed. And all we got to do is have a working put car. And this will just drop right in. You don't have to change a character. Okay, I'm just going to take a pointer to a string. The star dereferences the first character of the string, which in this case would be a P. And says, well, if P is not 0, then it's true. So we'll do the body. So we'll put the character that's the first character of the string. And then this plus plus moves to the next character in the string, which is now pointing to the O. So we'll just keep going that, walking down the string until we hit to the end. And there's automatically a 0, a null character put right here automatically in C code. And so when we do star stir and it ends up being a 0, now that's false, and the while is done and it falls on and returns from put string and does whatever's next.
Okay.
This one isn't particularly funny so much as
or practical.
Practical. But if you look up at the top here,
Okay.
you see, oops, sorry.
Is there any ever, like, how would we know how many ones are coming between our bits?
None. There is
None?
no ones. It's just one. It is just
Yeah.
a one.
Okay.
It's,
Like, could we
there's
keep
one.
track of the length of time between that then, or not really?
If you wanted to,
If you want.
don't have
There's
to,
just
though.
no need.
Well,
Okay.
you don't care. It's asynchronous. The whole point of the game is there is no,
Right.
like,
Yeah. Okay.
right? It doesn't have to be fixed.
Yeah.
So yeah, because it's just a one until it turns into a zero, and then once it's a zero, that's our start bit. There's our D, and there's our stop bit, which is going to be a one always. And then we got nothing left to send, so it just stays at a one until we get another start bit. And there's our data for that one, with a one as our stop bit, and so on and so on.
Cool. Okay.
And yeah, instead of it being 1, 1, 1, 1, 1, 1, it's really just one.
Yeah.
And then down here is a full duplex connection. You got to have a ground. They got to be on the same ground. So that's kind of something you got to watch out for when you're doing this kind of thing. If you're actually connecting two different machines together, they might be at very, very different grounds. It might not be pretty.
Yeah, and I guess if they're further away or something too, or if they're far away and you put the ground at one end or something, then
running on different phases of a three-phase, blah blah blah. Who knows, right?
Yeah.
So but in order for this to work, the data is like 3 volts above or whatever, or if you're just doing straight off the chip. You're doing straight off of the MSP432 straight into another MSP432. These voltage levels are 3.3 volts relative to ground.
Yeah.
If you're actually connected to the back of an old school RS-232 port, these voltages are well, they could be as much as plus and minus 25.
Oh, yeah.
You have plus and minus 25 up to your MSP432. Kaboom.
Yeah. Yeah. So our MSP232, whatever, whenever it sends data, the line when it's a 1 is staying at 3.3, right?
Yep.
And then drops to 0, and then 3.3 for
Yep.
Okay.
Yep. And depending, I don't know. I mean, that's the end of this one.